Mars has been a spot of attraction for everyone on Earth recently. You might have heard of organizations planning to go to Mars, but for just a normal person, what will that realistically look like? A lot of organizations have sent their probes onto Mars, and many more are planning. It has also been a favorite theme in movies, with Martians coming to our planet. But the reality is a bit different. Humans are the ones going to Mars and even capture it. The main question today is, how? And once we get there, how are we going to survive long term? The red planet's atmosphere is mostly carbon dioxide. The surface is very cold and the gravity is only about 38% that of Earth. All conditions not favorable for human life, but they can be changed. NASA has already announced its plan to send humans to Mars by 2030, and SpaceX plans to do so by 2024. But once we get there, we can use modern-day state-of-the-art technologies and models to terraform Mars. In this article, we will discuss how we will live and flourish on Mars. In the first section, we will talk about what happened to the red planet in the first place, and then how we will build habitation, grow food, and other necessities, and survive on Mars. Scientists believe Mars was very different from the way it is now. It had much more sustainable conditions for life before, with water flowing on the surface. Some even believe life might have existed on Mars before. The molten iron convecting in the planet's core generated a powerful dynamo that sent waves of magnetism emanating out from the planet. This magnetosphere protected the planet from solar radiation. It was a time when fresh volcanic activities started building up an atmosphere comparable to that of Earth. The heat trapped allowed the moisture to cycle around the planet as part of the hydrosphere, supplying water for rivers to flow, with a potential of biology. However, over a period of time, this magnetic generation stopped because of the cooling of the planet's core, and the planet was left vulnerable to the never-ending barrage from the sun. Eventually, the air was stripped away and the surface was exposed. The water retreated beneath the ground as ice, and Mars became barren as we see it today. But scientists have a model to bring back the lost magnetism of the planet. It is one of the hardest methods, but if scientists can figure out a way to execute it, 50% of all the other problems could be solved. We can supplement the magnetic field by placing a magnetic device at the Lagrange position of the planet. The competing gravity of the Sun and planet counterbalance one another, locking objects into a stable position between the two bodies. If enough magnetism can be generated at this point, a trail can be cleared behind for Mars to take shelter if we humans are in fact capable of working together to finance, design, engineer, construct, and implement such a device. With its magnetism recovering, the atmosphere will begin to build up and trap more air and heat. Pretty soon, dense clouds would rise over the Martian skies, providing the seeds of weather. Ice would dominate the contents of the clouds at first, coming to the surface as snow or frost. But with a building atmosphere, eventually water would converge in the air and fall to the surface as rain. This will mark the foundation of a water cycle. Eventually, we would see a flow of rivers and pools over the Martian surface. There is also another way suggested by scientists for tapping into resources of water. A solar-powered device which will use a special metal organic framework, MOF, to pull water out of the air in conditions as low as 20% humidity. This device can harbor about 3.2 quarts of water from air in 11 hours using 2 pounds of MOF. Such a device can be really helpful for making water readily available on the planet. The first step on terraforming Mars would be obviously reaching it at first. In the past years, we have witnessed the change in technology of landing used by NASA. Now many organizations are planning to land their landers and rovers on the red planet. Soon they will land humans too. But after reaching the planet, scientists will study the planet for solutions of residing on the planet long term. But what are the current models that have been proposed? Well, NASA is already on this problem, and there have been different prototypes for a sustainable habitat on Mars. The common idea among these prototypes are they will be self-sustaining, sealed against thin atmospheres, and capable of supporting life for a long time. Just like the ISS, which has taught humans a lot to survive in unfamiliar environments, Mars space stations will be a challenge worth taking. We'll need things like environmental control and life support systems, ECLSS, power systems, docking ports, and airlocks so that crews can perform spacewalks to repair things that break or to add new capabilities. Also, the trip to Mars will be a long journey. It will have psychological effects on astronauts, even though they are trained for this. To cope with this, these prototypes are supposed to have larger space for each astronaut. The scientists on the ISS who were in space simply needed more space. NASA also has a plan of keeping the base like an igloo, also known as the Mars Ice Home. It is an inflatable inner tube-like structure that would incorporate materials extracted from the planet and encased by a shell of ice. The idea behind using ice is that water is a very good shielding material against radiation. Radiation will be one of the most important challenges to solve on Mars. Those suits will be made more advanced, but also the bases. Prolonged exposure to the radiation can cause cancer or even acute radiation sickness. We can also build underground bases beneath the surface, but the ice base is a better option. The daylight will be able to pass through without making it like a cave. Mars is farther away from the sun than Earth and hence is cold. As mentioned above, without a thick atmosphere, unlike Earth, it is exposed to radiation and cold. Living on Mars will require special habitats that can provide warm temperatures and breathable air. Another challenge would be growing food on Mars. Keeping the food and medicine supplies stocked on Mars is the best way to make a habitat self-sustaining. But with a thin atmosphere and reduced sunlight, it can be difficult to get anything to grow. But there are some ways that scientists plan to grow food on Mars. Research suggests that Martian soil does contain some of the nutrients needed for growing plants. But because of the extremely cold conditions, they need to be grown inside a controlled environment. Just like Earth, nutrients may vary on the Martian surface from place to place. Inhabitants would need fertilizers to make the soil rich in nutrients. Fertilizers help farmers to double or triple their crop yields and contain 5% or more of primary plant nutrients. These fertilizers also supply nutrients to the crops that some soils do not have. Experts suggest using organic waste or manure to do so. Mars's atmosphere is mostly carbon dioxide, and plants need this gas just as much as we need oxygen to breathe. Also, studies suggest that watering plants on Mars could require less water than on Earth. That is because water would flow differently through the Martian soil thanks to the red planet's gravity, which is approximately 38% that of Earth's. This will allow the surface of the planet to hold more water and nutrients than the soil on Earth. Researchers are also developing sophisticated self-sustaining grow facilities to supply future astronauts with fresh fruits and vegetables. One such effort is being made by NASA in collaboration with the University of Arizona. It's also called the Bioregenerative Life Support System, or the BLSS. It's a hydroponic growth chamber that doesn't need soil to produce food. Bioregenerative life support systems are artificial ecosystems consisting of many complex symbiotic relationships among higher plants, animals, and microorganisms. It starts with water enriched with nutrients. This nutrient-enriched water supports the root system of the plants. The system is mutually beneficial to people and plants, as the former expel carbon dioxide, which is absorbed by the vegetation. The plants in turn produce oxygen as part of the photosynthetic process. When we think of Mars, we sometimes think of its future as greenhouses with plants and human civilizations colonizing with modern technologies. But those days are far away. It will still take a lot of time to terraform Mars. In the initial trips made by the scientists and astronauts, they will try to learn as much as possible about the planet. Since it differs greatly from Earth, survival is an important skill for astronauts to master. The initial base will probably include a habitat and a science lab. The inside of these modules will be much like the space station, but there will be differences. Microbial life is another threat to astronauts in space. Without more research, scientists cannot be sure that there isn't any dangerous microbial life that could threaten human life. Things will get more interesting once the base is established and astronauts learn the survival skills needed. then slowly we can focus on making the planet self-dependent on resources and necessities. Slowly, the farming and water harvesting will start. Using the above methods mentioned, scientists will try to terraform Mars and make it sustainable for living. Today, many enthusiasts like Elon Musk are already working on making Mars a permanent human colony, and they have a goal to send about 250,000 people to Mars and set up a Martian colony. In the coming years, we will see the first person on Mars and soon a colony. The technologies will be more advanced and even change, but one thing is guaranteed: a bright future for space exploration. Why do we spend so much time looking for life on Mars when the red planet has had liquid water for only 400 million years? While here, 2 steps, there is Venus that has hosted oceans for 3 billion years and no one considers it. Do you think we overlooked a little too much the planet that before the space age was still considered fit for life and perhaps covered by oceans? Since the mid-1990s, U.S. scientists alone have submitted nearly 30 Venus proposals to NASA. None have been approved. It was during the space race that scientists discovered on Venus a torrid and toxic world. That could explain why interest in Venus dwindled. Scientists quickly realized that this planet would not be a home for future human exploration, nor an outlet on which to search for life. It would be downright difficult to study at all, even for short amounts of time. But the wind is changing, which was due to the controversial finding of phosphine in its atmosphere. Lately, the interest in the twin sister of Earth has been increasing, and NASA has finally approved new exploratory missions. More and more planetologists are hypothesizing for Venus the possibility of terraforming, even more than Mars. Like Mars, Venus was once a vastly different place. According to data gathered by various missions, it is believed that until 700 million years ago, Venus was a warm and wet planet where oceans covered 80% of the surface. This is actually close to what scientists thought Venus was like until the Soviet Venera and NASA Mariner probes revealed what a hellish place it is today. This came to an end apparently due to a near-global resurfacing event that occurred 500 million years ago, where large amounts of magma bubbled up from the mantle and released massive amounts of CO2 into the atmosphere. This magma would have solidified before reaching the surface and created a barrier preventing the atmospheric CO2 from being reabsorbed by the crust. What followed was a runaway greenhouse effect that caused severe climate change, leading to the hostile environment that we see there today. However, if the planet could be restored to its former self by reversing the greenhouse effect, which is possible, then humanity would have a planet closer to Earth that is roughly equal in size, mass, and gravity. Let's compare. Venus is the closest planet to Earth, ranging from a minimum distance of about 38.2 million kilometers to a maximum of around 261 million kilometers. Because of the nature of our orbits, Earth and Venus make their closest approach every 584 days, 1 year and 7 months, which is known as an inferior conjunction. In contrast, the average distance between Earth and Mars is about 225 million kilometers, ranging from 55.7 million kilometers to 401.3 million kilometers. Our 2 planets make their closest approach every 26 months, 2 years and 2 months, which is known as an opposition, since the Sun and Mars are on opposite sides of the sky when viewed from Earth. So not only does Venus get closer to Earth than Mars, but it also makes its closest approach to us more often. This means that missions to Venus could launch more often and would take less time to get there. Then there's the matter of Venus's gravity, which is the equivalent of 90% to what we experience here on Earth. Compare this to Mars, where the gravity is roughly 38% of Earth's. This means that for potential settlers, the health-related risks associated with lower gravity would be much lower. Of course, Venus, as it is today, has its share of challenges that makes the prospect of living there very difficult. These make terraforming not only a good idea, but a potential necessity, assuming people want to live there in large numbers. Otherwise, they will need to be happy living in floating cities among the clouds, an actual possibility. For starters, Venus is the hottest planet in the solar system, with an average surface temperature of 464 degrees Celsius, which is hot enough to melt metals like lead and zinc. The atmosphere is also a toxic fume, composed overwhelmingly of carbon dioxide, with trace amounts of nitrogen, sulfur dioxide, and water vapor. However, unlike Mars, Atmospheric pressure on Venus is 90 times the pressure of Earth's atmosphere. To experience that kind of pressure here on Earth, a person would have to venture over 910 meters under the sea. So unless you have a vehicle that can withstand extreme heat and pressure, you're not getting anywhere near the surface. As if that weren't enough, Venus's atmosphere is also permeated by clouds of sulfuric acid rain. These have been observed in Venus's upper atmosphere and may not condense closer to the surface, but spacecraft attempting to land on the surface must first penetrate this acidic shroud. Venus also has the slowest rotation period of any major planet, taking roughly 243 Earth days to rotate once on its axis. On top of that, Venus rotates in the opposite direction as the Sun, retrograde rotation, which is something astronomers have only ever observed with one other planet, Uranus. Between its slow retrograde rotation and the fact that Venus takes close to 225 days to orbit the Sun, a single solar day on Venus lasts 116.75 days. This means that for an observer on the surface of Venus, it takes close to 4 months for the Sun to set and rise again, compared to 24 hours here on Earth. Venus is also isothermal, which means that it experiences virtually no variation in temperature. This is due to its dense atmosphere, but also its slow rotation and its low axial tilt, 3 degrees versus Earth's 23.5 degrees, which essentially means that Venus doesn't experience seasons or anything we might consider a day-night cycle. If you're thinking that this is starting to sound like something out of Dante's Inferno, then you're on the right track. But with the right kind of work, it could be made into something more akin to a tropical island paradise. Luckily, with the right kind of ecological techniques and some serious elbow grease, Venus could be terraformed into an ocean planet with mild temperatures and endless beachfront property. As with Mars, it comes down to 3 major goals. They include reducing the atmospheric pressure, lowering the temperature, converting the atmosphere to something breathable. Much like terraforming Mars, these 3 goals are complementary, even if they are the complete opposite. Luckily for us, Venus has a lot to work with, and the outcome would be easier for humans to adapt to. The first proposed method was made by none other than Carl Sagan in 1961 in a paper titled The Planet Venus. It was in this paper that Sagan argued that seeding the atmosphere of Venus with genetically engineered cyanobacteria could gradually convert atmospheric carbon dioxide to organic molecules. Unfortunately, the subsequent discovery of sulfuric acid clouds and the effects of solar wind made this proposal impractical. It would be another 30 years before another proposal for terraforming Venus was made, which was done by Paul Birch in his 1991 paper, Terraforming Venus Quickly. According to Birch, flooding Venus's atmosphere with hydrogen would trigger a chemical reaction, creating graphite and water. The graphite would be sequestered while the water would fall as rain and cover 80% of the surface in oceans. Another proposal is to use solar shades, something that was recommended by Birch and famed aerospace engineer and space exploration advocate Robert Zubrin. This concept would involve using a series of small reflective spacecraft in Venus's atmosphere to divert sunlight, thereby reducing global temperatures. Alternately, a single large shade could be positioned at the Sun-Venus L1 Lagrangian point to limit the amount of sunlight reaching Venus. This shade would also block solar wind, preventing Venus's atmosphere from being stripped and also shielding the planet from solar radiation. This would trigger global cooling, resulting in the liquefaction or freezing of atmospheric CO2, which would then be deposited on the surface as dry ice, which could be shipped off world or sequestered underground. Another suggestion is to speed up Venus's rotation, which could have the added benefit of generating a planetary magnetic field. There are a number of ways to do this, like striking Venus's surface with large asteroids or using mass drivers or dynamic compression members to impart transfer energy and momentum to the surface. This would allow for the creation of an Earth-like diurnal cycle and could also help remove some of Venus's dense atmosphere. Similarly, mass drivers or space elevators could scoop clouds from Venus's atmosphere and eject them into space, gradually thinning it out over time. The end result of this would be a Venus very much like its former self. This would mean a planet covered predominantly by oceans, Due to the nature of Venus's geological features and small variations in elevation, the surface would essentially be a giant archipelago with a few larger continents. Over time, humans could introduce terrestrial organisms like plants, trees, bacteria, and aquatic species to Venus. With some modifications, this could lead to an explosion of life and the development of a tropical planet with biodiverse jungles on the larger landmasses and more coastline than you can shake a stick at. Okay, you may have already figured out what the downside of all of this is. If you guessed that it would take a massive effort to transform Venus, and it would be very challenging to create a settlement there in the meantime, you'd be absolutely right. While Venus could be terraformed to become what it once was, the commitment in time, energy, and resources would be nothing short of Herculean. Beyond the similarities Venus has with Earth in size, mass, and composition, there are numerous differences that would make terraforming and colonizing it a major challenge. For one, reducing the heat and pressure of Venus's atmosphere would require a tremendous amount of energy and resources. It would also require infrastructure that does not yet exist and would be very expensive to build. For instance, it would require immense amounts of metal and advanced materials to build an orbital shade large enough to cool Venus's atmosphere to the point that its greenhouse effect would be arrested. Such a structure, if positioned at L1, would also need to be 4 times the diameter of Venus itself. It would have to be assembled in space, which would require a massive fleet of robot assemblers. In contrast, increasing the speed of Venus's rotation would require tremendous energy, not to mention a significant number of impactors that would have to come from the outer solar system, mainly from the Kuiper Belt. In all of these cases, a large fleet of spaceships would be needed to haul the necessary material, and they would need to be equipped with advanced drive systems that could make the trip in a reasonable amount of time. Currently, no such drive systems exist, and conventional methods, ranging from ion engines to chemical propellants, are neither fast nor economical enough. To illustrate, NASA's New Horizons mission took more than 11 years to make its historic rendezvous with Pluto and the Kuiper Belt, using conventional rockets and the gravity assist method. Meanwhile, the Dawn mission, which relied on ionic propulsion, took almost 4 years to reach Vesta in the asteroid belt. Neither method is practical for making repeated trips to the Kuiper Belt and hauling back icy comets and asteroids, and humanity has nowhere near the number of ships we would need to do this. The same problem of resources holds true for the concept of placing solar reflectors above the clouds. The amount of material would have to be large and would have to remain in place long after the atmosphere had been modified, since Venus's surface is currently completely enshrouded by clouds. Also, Venus already has highly reflective clouds, so any approach would have to significantly surpass its current albedo. That on a scale from 0 to 1 is worth 0.65 to make a difference. And when it comes to removing Venus's atmosphere, things are equally challenging. In 1994, James Pollock and Carl Sagan conducted calculations that indicated that an impactor measuring 700 kilometers in diameter striking Venus at high velocity would result in less than 1,000th of the total atmosphere. What's more, there would be diminishing returns as the atmosphere's density decreases, which means thousands of giant impactors would be needed. In addition, most of the ejected atmosphere would go into solar orbit near Venus, and without further intervention could be captured by Venus's gravitational field and become part of the atmosphere once again. Removing atmospheric gas using space elevators would be difficult because the planet's geostationary orbit lies an impractical distance above the surface, where removing using mass accelerators would be time-consuming and very expensive. In the end, the potential benefits of terraforming Venus are clear. Humanity would have a second home. We would be able to add its resources to our own, and we would learn valuable techniques that could help prevent cataclysmic change here on Earth. However, getting to the point where those benefits could be realized is the hard part. Like most proposed terraforming ventures, many obstacles need to be addressed beforehand. Foremost among these are transportation and logistics, mobilizing a massive fleet of robot workers and hauling craft to harness the necessary resources. After that, a multi-generational commitment would need to be made, providing financial resources to see the job through to completion. Not an easy task under the most ideal of conditions. Suffice it to say, this is something that humanity cannot do in the short run. However, looking to the future, the idea of Venus becoming our sister planet in every way imaginable, with oceans, arable land, wildlife, and cities, certainly seems like a beautiful and feasible goal. The only question is, how long will we have to wait?
Indeed, you've heard a lot about terraforming Mars, but little about the Moon, and it's normal to hear about bombarding it with water-filled meteors as if this would be an easy task, looking to turn it blue and then green. But how true is this? What can we do to terraform the Moon, and is it viable? Let's find out. Challenges and resources required to terraform the Moon. Working on terraforming the Moon has one significant advantage over any other planets in our solar system: distance. Compared to Mars or Venus, the most common candidates, you can communicate practically in real time with people on the Moon. The logistics necessary for the task are greatly facilitated. However, not all of them are advantages, because each planet or the Moon is different. To live anywhere on the universe requires us to fulfill specific basic needs: food, water, breathable air, and shelter from radiation. This means that the first thing we need is an atmosphere, something that the Moon in principle does not have, because of the solar wind that would sooner or later rip apart any gases that could form on the surface. The lunar magnetic field. The first thing that must be solved is the absence of a magnetic field so that the solar wind won't snatch away any of the atmosphere that we can create. Since our satellite is tiny and has no active tectonic plates, thinking about activating or reactivating a dynamo in its core is not a good idea. Instead, a high-powered magnetic field generator can be installed to enter a parallel, fixed orbit concerning the Moon. This can be achieved by placing this magnetic generator at the first Lagrange point, which is an area in which the gravitational pull of celestial bodies is counteracted so that an object spiraling downward to the Sun can be maintained as a fixed point in space by being pulled by other bodies such as the Moon and Earth. This equipment would require large amounts of energy, but large solar panels can provide this since they would be most effective where there is no atmosphere. At the same time, that could facilitate us to install a series of mirrors that can concentrate the Sun's energy towards the Moon, giving us an abundant source of energy for the activities we must do on or beneath the surface. Another need that this achievement would cover would be an improvement in the quality of human life throughout the process, since solar wind and the radiation that it brings can very negatively affect the health of astronauts after prolonged exposure, even increasing the odds of cancer. Water, atmosphere, and temperature. Once we don't have to worry about the solar wind and radiation, we can concentrate on forming a lunar atmosphere and carrying water to the Moon. It should be clarified that causing meteorite impacts can be a terrible idea. First of all, while in theory you could make controlled impacts of meteors rich in water or other materials that we need, the logistics of going to an asteroid belt and accurately diverting one from its existing gravitational path makes this solution very expensive and excessively slow. No, we need something faster. Suppose the calculations go wrong or certain factors are not considered when modeling the impact trajectories towards the Moon. A lousy collision could expel gases, water, and materials into space, losing the atmosphere gains and all the time it took to accomplish. Not to mention that it could put human lives at risk. Turning to see the Moon's resources may be a better idea. For example, during the last decades, it has been detected that the Moon has water in the form of ice on its surface, especially in those areas where sunlight does not reach, such as craters or shadows generated by the rocky relief, something that has been suggested by multiple investigations. Still, it has also been shown that lunar rocks collected in the Apollo missions are hydrated, so you could get water from these, as according to Alexander Basilevsky, a planetary geologist at the Russian Academy of Sciences. Suppose we can take advantage of the sun's energy with solar panels and burners. In that case, we can obtain energy to carry out electrolysis processes with lunar rocks and gradually take the elements that we have at hand on the surface. In their latest Unified Geological Map of the Moon, the United States Geological Survey, or USGS, in conjunction with NASA, has interpreted a silicate-filled surface where getting oxygen wouldn't be a problem. If you have a lot of oxygen in the rocks and lunar regolith, you can use the hydrogen from space to create water. The process is what Alexander Vasilevsky mentions as the first water former on the Moon. However, this water could be volatile and easily escape into space by being bombarded by the Sun's high-energy particles, disintegrating the water molecules back into hydrogen and oxygen, unless they can find refuge in craters and permanently shadowed areas of the Moon where ice sheets are thought to be found, from the poles to the equator, which can provide a precious resource relatively at hand. Also, these electrolysis processes will necessarily involve a generation of heat to the environment. So, when we create or capture oxygen and water, we could be releasing heat relatively slowly but safely. We have already experienced a warming planet after all. One problem that remains to be addressed is the little presence detected in the lunar rocks of nitrogen and carbon, essential elements for life, and found only in parts per million on the Moon. However, this could be not entirely true, since the samples we have are not from the entire Moon, which can cover up local rock deposits that do not have these elements, an idea that is gaining strength, since it has been detected that samples of carbon ions are being emitted in more significant quantities than expected in the basaltic mines, according to the data from the Japanese mission of the lunar orbiter Kaguya. If this is confirmed for carbon, it would give us hope for nitrogen or facilitate logistics by importing fewer elements into the lunar atmosphere. Gravity. The main problem of planetoids and satellites in terms of terraforming is their lack of gravity. It is usually fantasized about a full moon of water and waves 20 meters high with people who can fly with little equipment due to the low gravity. A lunar Florida, as it were, but currently this is only a fantasy. In reality, low gravity has two serious problems. The first is that it involves health problems for settlers or future inhabitants, although we do not know this for sure. Many astronauts have experienced shallow gravity on the International Space Station or in space traveling. Still, the Moon has gravity, 1/6 of the Earth's, but it is better than nothing, and the effects of bone and muscle loss may not present themselves in the same way. Despite that, you can kill two birds with one stone by placing pieces of lead in astronaut suits to increase their weight and protect them from radiation. Or you can decrease this problem with plenty of exercise and special facilities for sports and sleep, facilities that keep the body feeling the Earth's gravity when sleeping. However, the real problem of low gravity in terraforming is much more severe, since combined with solar wind, it prevents the Moon from retaining the gases with which we would build its atmosphere. It has been estimated that we could only retain them for about 10,000 years, forcing us to create a giant dome that keeps the atmosphere contained inside, or constantly generates new gases to replace those that escape into space, a problem that greatly complicates any immediate hopes for terraforming. On the other hand, maintaining the idea of bombarding the Moon with meteors, asteroids and comets to make it gain mass and better retain a future atmosphere not only increases the risks already mentioned above, but perhaps it would not be a good idea for life on Earth if our satellite has more and more mass. Increasing it would attract more meteors and asteroids. In addition, the effects on the tides could be devastating, affecting the lives of many human beings who live on the coasts and the value chains of energy infrastructures, enlarging the problem in large quantities. So, if there is no way to make the Moon have more mass and the atmosphere will be lost anyway, is it even possible at all to terraform the Moon? No, at least not with current technology. But there is no need to give up hope just yet. Lunar colonization. As we theoretically face the challenges of lunar terraforming, researchers have found more and more objects of interest both in a scientific sense and an economic one, and the Moon may still have many untold secrets. We must remember that the Apollo missions were motivated by politics rather than science, which meant that the landing sites did not have planning that favored scientific research. Hence, knowing better the resources that the Moon has is fundamental. There is already a program of lunar exploration, exploitation, and commercialization working hard to return to the Moon and conduct experiments that test what has been found so far, and commercial arrangements like the Artemis program, led by NASA, but in which multiple space agencies participate. Suppose the logistical capacity to exploit lunar resources is achieved and economically worthwhile deposits such as rare earth elements are discovered. In that case, this program will grow and competition may arise, starting with space mining. If this happens, creating industry and human habitats to operate these industries will become a priority, and we will apply everything learned to generate these habitats. Perhaps in large craters we can install a dome, take advantage of the water they have, and import some land, carbon, and nitrogen in specific areas for the livelihood of workers through a lunar crop. Solar panels, heaters, and ovens can be used to generate enough energy. Additionally, mining on the moon will carry out the electrolysis processes. Since the days last for weeks on the moon, another option to create shelters for humans would be to dig out caverns a few meters deep where, during the day, there will be naturally a pleasant temperature for humans. We can take advantage of energy stored during the day and at night. These activities may gradually extend until colonization is an undeniable fact. This colonization has other advantages in addition to the economic ones, since the moon can be used as a base of space operations to other satellites and planets, as the low gravity entails a lower cost for any launch. The necessary infrastructure will begin to exist due to the economic needs anyway, making this proposal even more profitable in theory. The in-situ resources, and especially the water reserves that the moon has, will facilitate the production of rocket fuel if we continue with the same technology in the first place. At the same time, there is a planet that is very similar in many ways to the moon, but that has greater gravity and a much greater energy supply. A planet on which the same techniques that we have explored can be used and would have greater possibility of being terraformed: Mercury. Working on lunar terraforming will make us gain experience and open the door to terraforming of other similar satellites, where the solar wind and gravitational context are more beneficial for the task, expanding in turn the potential of space mining. Perhaps we can't terraform every celestial body in our solar system, at least not for now, but achieving it would be the most remarkable human feat. Finally, the human being would be taking the first steps in the right direction to become a space colonizing species. It will take time to get used to these activities. And while we should never look down on ethical and social questions, colonizing the moon until self-sustainability in artificial habitats is possible. It is the necessary next step for our survival, and at the same time, the natural next step for our species.